Okay, so we'll as I told, we'll start with module 3. So this module deals with embedded systems. Starting from here, module 3, module 4, module 5, all these deals with embedded systems. Okay, in this, so we'll start with the embedded system components, and the first part of this module is about the introduction, more or less introduction, and then some the background of the embedded systems. And the second part of the module is the components. Okay, so we have different components in embedded systems. We look at the different components like processors, input and output devices, and firmware and other things. Okay, so now let's get going. Okay, so now we will look at the introduction to embedded systems. So what is an embedded system? Okay, so any idea you guys have about embedded system? What embedded system is? And like I said, if some question is asked, it will be really good if you guys respond. So I think it's also kind of a feedback, so that I know that you guys are listening, and then I'm not uh, I mean, let's say my mic is not working, right? How will I know? So at least it will be good if you can respond saying yes, no, or things like that. Okay. Okay, so what is an embedded system? Anybody? Okay, let's go back to your yeah, I may have to so how many of you saw this video before? I mean, I have posted a YouTube video on this. Did anybody get a chance to look into that? Okay, I assume not. So we'll quickly see what is an embedded system. So as the definition goes like this: it is an electronic or electromechanical system designed to perform a specific function, and is a combination of both hardware, firmware. Firmware is nothing but it's kind of a software. Okay. Right. Yeah. So the point to note here is that this embedded system is it's an electronic or electromechanical system. It's not like your general purpose computer, like your laptop or PC. It's more towards an electromechanical. So it also has some extra components to it. uh, an example for this is say a lift, an elevator, right? If you take that as an example, it's not just a computing device, right? It's not, but it does have your microcontrollers and your keypads and things like that. But it is not a completely, it's not like a general purpose computer. You can't do computation using that. And then it's designed to perform a specific function, meaning your there's a specific function associated with your lift. Your lift is supposed to take a person from one floor to the other, so that's the sole purpose. So its purpose is not computing. Okay, so the actual purpose of an embedded system is not about computing. It is it's used to help some other system. Okay, and automate or to make its performance better. Okay, ease. So a typical example is lift. So the function of the lift is not computing, but then you still use embedded computers on that. Okay, and it's combination of both hardware and firmware. Okay, so it does have hardware components to it, and then it also has software component to it. So the software here is mostly, it's referred to as firmware, because these softwares are not like that easily programmable. So they are mostly they rely on ROMs, like read only memories. So you write your programs onto the ROM, and then you once you install it, you rarely see any change in that. Again, if you take the lift example, we don't see often that somebody coming and then updating the software, right, of the lift. It actually does have a logic or a software or a process running. But it's a very small process, but it still has a software component to it, but we don't see it itself getting updated quite often. So that's why it's called as a firmware. Okay, all right. So then we'll look at what are the different places where we can see this embedded system. So they are almost like everywhere. It's kind of ubiquitous. You pick anything these days, you see an electronic component behind it. So for example, like household appliances, you have your fridge, and then you have your microwave oven. All these have embedded system into it, or it has like a some kind of computing power to do something little smarter. And then in telecommunications, of course, we have your cellular phones, and also your normal dial phones, right, like the landline phones. So they also have embedded components into it. And then we have medical equipment like your EEG, ECG, all these things. Then industrial control, so we see all these industrial process automation, right? So those also are controlled ultimately by these embedded devices. And we have consumer products, so we have your other things like your game consoles, and your digital cameras and things like that, and DVD players, things, all these things. So anyway, and there's much more. Like I mentioned, nowadays, like in this modern world, right? So it's rarely we see something that's not an embedded device. Things are getting smarter and smarter these days. Okay. So then I was talking about the embedded system versus general computing systems. So in embedded, so we'll see what are the differences. So we have your general purpose computing system here, and the embedded system on the other side. We'll start comparing these. So first of all, like we saw, a general purpose system is, as the name suggests, is for general use. Okay, it has a general purpose operating system, and it has a generic hardware, and it can be used for multiple applications. It's generic. A typical example is your PC or your laptop, right? So you can install whatever software you want on your laptop, and you can customize it as per your need. But in an embedded system, that's not the case. It, as we saw, it is designed for a specific purpose. And the second point is, it contains a general purpose OS. Here it may not contain OS at all. Okay, so the like we saw in, let's say, let's take lift again. In that, we don't see any operating system. We don't see any OS or anything in that. But having said that, there are lots and lots of embedded systems that have operating systems, but these are not general purpose operating systems, but these are called as real time operating system, or RTOS. Okay, RTOS or RTOS, that's what they call. Examples of this includes your cars, your cars, and especially the modern cars, right? So they have their own firmware, and on top of that, they have their operating systems, everything running. But these are real time operating systems. The other example will be like your flight control system, or nuclear power plant system, or even industrial automation system. So these are like really large scale embedded systems. They have these operating system, but these are very it's a real time OS, and it's specific for that use. Third point is, applications are alterable or programmable by the user, and I think we are already aware of this, right? So in your laptop or PC, you can install or you can update your applications as and when you go by. But that's not the case. Like we saw it, the most of the embedded systems have only firmware, and it's in most cases it is not alterable at all. And even if it is alterable, it's ROM, so it takes a while. You need to take the device to a particular service center and then get it updated. You cannot have like a on the flow updates. Okay. Next one is performance is the key. Faster is better here. So in general purpose systems, that we know. So when we buy laptop, we always look for the high end computers, like latest processors, updated graphics card, a very large RAM, and then you want it to be really fast as it is, right? But that's not the case with embedded systems. You may wonder, like, why would somebody not have faster performance, right? But performance is not the key here. If you take embedded devices, embedded systems are mostly handheld or battery operated, so you don't need like a performance. It's not performance oriented. As long as you meet some deadlines, it is fine. I'll give you an example. We'll again pick the lift example. You're just pressing the number 3 on the lift, and then it's there's no like hard and fast thing that it has to be like so fast, right? So as long as it meets the user satisfaction, it is good enough. Like within a nominal amount of time, if the lift starts operating and it takes you to the floor 3, then you're good enough. You don't need like a very fast computer there. And second thing is, so ultimately most of these embedded systems are battery operated, and their power uh, 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 constrained. So you have this power or performance as the power and energy as your primary criteria. uh, Again, an example of this would be, say, your smartwatch or any other handheld device. You don't want to recharge them every time, right? So you want to have as long a battery life as you can. So here, apart from performance, your power is also a very important factor. Point number 5 is less or not tailored towards reduced operating power requirements, options for different power settings. So here you can play around with it. So even if you take your laptop, you have your low power mode, and then you have your high performance mode, and there's a balanced, and there's some all the things in between, right? So there's a you can play around with all these settings. So you can customize your laptop for a particular performance or power setting. But here it's not. So once it's done, it's like mostly it's power constrained, and there are no different modes that you can play around with, and it's mostly like power saving mode. And finally, you have your so yeah, point number 6 is response time is not critical, and here response time is critical with hard deadlines. So in your laptop, you don't really care about your response time. You do, but then it's not going to affect you in any way. Meaning, let's say you are clicking onto some like a browser or something, and then it spins. Okay, not responding, right? It spins for a while, and then you just wait. Of course, the user satisfaction is affected, but nothing else is impacted. So hardly it's going to take whatever would have taken you 1 second. It might take like 10 seconds or half a minute. But then other than that, we are not losing much, because the way that the kind of applications that we run. But however, you when you check with embedded systems, that's not the case. If you take the lift again, for example, I mentioned that you press the key, and there's a nominal amount of time you wait. But then the nominal time should not be excess, right? So it, as the name suggests, it's nominal. So you press the floor 3, and then the lift better starts working within 1 or 2 seconds, isn't it? Otherwise, you are actually, you think you're stuck in the lift, isn't it? So there are deadlines here. But here, in this particular lift example, the deadline is not a hard deadline. So in many cases, embedded systems have hard deadlines, but in other cases, it's not hard deadlines. It's called soft deadlines. Like for example, lift is a soft deadline system. The lift taking some extra time is not going to affect anybody's life or anything. But if you take your ABS or anti-lock braking system in your car, right? So that's an embedded system. And when you press the brakes, so when you press the brakes, it's not like in earlier days where you directly work on your hydraulics. Okay, so it actually connects to an ABS, and it's more like you're actually driving a remote controlled car or a video game steering, right? Steering and brakes. So you press this brake, and then it sends signals to this embedded computing device, and then that embedded system is going to apply the brakes appropriately to the hydraulic. and then it gets so that's why there's a coupling between your electronic and your mechanical, so it's electromechanical. So in that case, right, so the response time is very critical. The moment you apply the brake, within the matter of 1 or 2 seconds, the brake better, actually 2 seconds is still very high. So actually you deal with millisecond, hundreds of milliseconds, the moment you apply the brake and the moment the brake actually gets applied, right, so that time is very critical. And if there is any delay in that, if you fail to meet the deadline, it may lead to disaster, somebody's life may be at risk, or the property may be at risk, right? So those, so the embedded system have those kind of constraint here. It's very very strict with deadlines. And finally, we have execution behavior need not be deterministic. So again, it couples with the previous point. So like you said, you never know when you click on to some browser and then it will go spinning, or you open some kind of some kind of a window and then it says, no, we can't open it, some update is needed here in your operating system is installing updates, and then it starts spinning, right? So you never know when these things will happen. And even if this happens, it's, you're okay with it, meaning you'll get frustrated, but it's not going to affect anybody's life or anything. But here it has to be deterministic. So when I apply a brake, I should know that it has to apply the brake. Okay. Again, even severe examples, like even more critical examples includes your flight control system, right? When you have your pilot saying, okay, flaps on, your flaps better gets on right away, right? You lift the flap, you have the flap should lift. So it's like that. So within small time, and it has to be deterministic. It cannot say, okay, no, I'm installing update, we'll actually bring up the flaps after the updates are installed. So you can't have that kind of a behavior here. Okay, any questions so far, guys?
No, sir.
All right, great, nice. Okay, so let's talk about the history of embedded systems briefly. So embedded systems are not like the buzzword. It's not like some new thing that we are seeing. Rather, it's actually, it existed even before IT revolution. In fact, it existed even before that, like even before even your silicon revolution started. So early embedded systems were built on vacuum tubes, and then they transitioned over to the transistors. Okay, so one of the earliest embedded system was your AGC, Apollo Guidance Computer. If you guys know about the moon mission, right? The mission, the lunar mission. So they used an embedded system, embedded computing device there. So it's called as an Apollo Guidance Computer, or AGC. So it mainly had two modules. So one is the command module and one is the lunar excursion module. So it's similar to even what we have in our Chandrayaan, right? Even in a Chandrayaan 2, if you remember, we had these two modules. So one that will orbit around the moon. So that's your like lunar. Sorry, that's your command module, and the other one is your lunar excursion module, which actually lands on the surface of the moon. So both these, right? So they had your AGC on that. And if you think it could be some kind of a hi-fi computing device, no, it's not. Okay, so it only had this 4K words ROM and 256 words RAM. So ROM is your fixed memory. So it's a read-only memory. You cannot alter it. And your RAM is the erasable part, right? So it's a programmable memory here. So you can see how small it is. And later it was upgraded to 36K and 2K respectively. So that's the size of your memory there. So we now so you can compare this. This is 2K, and then now we have even 2 GB of RAM is a very less number these days, right? So and then coming to the frequency, it operated at a huge 1 megahertz clock, right? And then which was actually pulled from a I mean one megahertz clock, which was pulled from a 2 megahertz crystal clock. So that's the speed of your device right there. Okay, and it had again like whopping 11 instructions, and this is 16-bit processor. Okay, so that's about it. Okay, 11 instructions running at 1 megahertz, working on a 4K and 256 word RAM. So that's what took us to moon. Okay, so now we have around approximately like 5,000 ICs that was supplied by Fairchild Semiconductor. Okay, and we also had a user interface unit. It's called as DSKY, or display keyboard unit, and so it looks like this. So if you can see, right, bottom picture here, so that's your computer. That's your AGC right there. That took us to moon several times, not once, right? Multiple times. So that's an important. I mean, so that's a very interesting thing, right? So that's the power of this embedded computing. See, you don't need like a very high performance thing. So as long as you can do some control operations and you can meet up to your requirements, it's fine. Okay, but anyway, so in those days this was actually reasonably a good configuration. That's true. So this was in so AGC was first designed in 1963, right? And then first lunar landing happened in 1969. Okay, so that's briefly about the I mean the history part. Yeah, this happened long time ago. All right, now coming to classification of embedded systems. So based on the embedded system are classified based on your generation or complexity and performance requirements, deterministic behavior, and then triggering. Okay, so we look at the last 2 points now. So deterministic versus non-deterministic behavior. So like I mean we saw earlier, right? So that's one of the differences between a general purpose system and an embedded system. So your embedded system can still have like a non-deterministic behavior like that, but those will be like a very non-critical embedded system, right? But then there are most of the embedded system fall under this deterministic behavior, which means that it cannot go wrong. So if I press a button 3 in my lift, it has to take me to the floor 3. Okay, it cannot take me to floor 4. Or and the other thing is it has to take me to floor 3, and it cannot do something funny like open and close the door, right? So it shouldn't be very uh, what to say, non-deterministic, of course. And next we have, so coming in line with that, right? So we have something called as hard versus soft execution behavior. So this is your deadlines. Okay, so your hard versus soft deadlines. So hard deadlines are those that are associated with critical applications, like we saw, right? Airplane, so aircraft control systems, or your car, automotive systems. If you take all these or industrial automation, so these have hard deadlines, which means within span of certain time you have to take an action, otherwise it may lead to a catastrophe. The other things are soft deadlines. If you take examples, this will be your like your calculators, or your lift, and or even toys, right? So so those are like soft, they have soft deadlines. Maybe even your DVD players, they don't have like a very hard deadline. So you have a frame rate, or a disk spin rate that you want to uh, I mean you have a requirement for that, but then not following the deadline will not lead to a catastrophe. So that's the idea. So now classification based on generation. So now you have your different generations. So the first generation was 8-bit microprocessor or a 4-bit microcontrollers. So the examples of these are early digital telephones, right? And then you have your stepper motor control unit. So these were the very early embedded systems. And then in your second generation you have 16-bit microprocessors and 16 or 8-bit microcontrollers. So these were the DACs and SCADA systems. So your DAC is nothing but these are the data acquisition systems that you connect to your hardware board, like your motherboard or something, right? So then you can actually pull some signals out of it. So it's something like what you see in your what you connect your oscilloscopes to, right? So you connect it to these circuit boards. So those were the racks, and then you have your supervisory control and data acquisition systems. These are SCADA systems. So these are the control systems that are used in large scale factories and industry power plants. So there you have your automation, right? So if, I mean, I'm sure you would have seen some nice videos about how things are made in factories, right? Like how chocolate is made, how your your erasers or pencils are made. So you see these lots of highly automated synchronous automated systems in power plants. So there you have these control systems. So those are the supervisory data acquisition systems. Third generation includes your DSPs. So these are like 32-bit microprocessor or 16-bit microcontrollers. So the digital signal processors, many signal processing like video streaming, audio streaming, all these signals, right? So those come under this. And you also have application specific integrated circuits. So these are ASICs. These are they are not like a general purpose microprocessors. It's actually you don't have a general purpose processors there. These processors are specifically designed for a particular application. So it will be something like a nuclear power plant control system, right? So where you have specific requirements of the power nuclear power plant, and you will design a processor for that. So the examples of this include your robotics and your media, and then your industrial process control and networking. And then we have our fourth generation. So these are system on chips. So now your fabrication industry has become so well and advanced in technology that you have shrunk the processors. So you can put all your CPU, your cache memory, and then your display system. When I say display system, it's not you're not going to put a display there, but it's the control system for the display, right? Like that. So display system and your audio control system. And some encryption units and all these things, and lot of ROMs. So all these things are all these different devices are going to fit into a single chip. And the chip size, if you think about it, it's just going to be the size of your nail of your thumb. Okay, it's going to be like some like it's like 1.5 centimeter by 1.5 centimeters, like that, half an inch. It's like half an inch, half square inch kind of thing, right? So it's that small. You can actually put all these devices, all these components into one chip. And we also have now these reconfigurable processors and multi-core processors. So the reconfigurable processors are these FPGAs where you can program a processor. So if you want to change the pipeline, you can actually change by reconfiguring the processor. I mean, technically that is possible. And your multi-core processor, of course, you guys know all our smartphones are octa-core now, and even your laptops are multi-core, right? Like so even this has come to the embedded devices. Your embedded devices now have multi-cores. So examples of this include your smartphones, and then your mobile internet devices and things like that. Now, is there any fifth generation? If you think about it now, what's next? It's going to be like embedded devices almost like everywhere. So we are talking about Internet of Things. So where anything that you think of, right, can become smart. You think of your uh, let's say lights. We have your smart lights there. And you think of your water supply to your home. You have smart water meter. And you can just think of anything, and you have embedded systems attached to even farmlands, right? You attach that to the trees and your farmland too. You put it on a soil. So you can just think how ubiquitous it's going to get. Okay. uh, Classification based on complexity and performance. So you have small scale, where these are very low cost, like cheap calculators and digital watches, things like that. So they are not very critical. They have non critical performance requirements. And the second one is your medium scale. These could have some DSPs, your like your DVD players, your digital TVs, your cameras, digital cameras, your cell phones, like that. So they come under the medium scale, and then you have your large scale, where these are highly they have complex hardware and software requirements. This is and they may have very critical requirements. So these are your automotive systems, your braking systems, and things like that. So to give you an idea, right, so you take the modern cars. These modern cars actually have from hundreds to thousands of microcontrollers. So hundreds to thousands, I'm not even exaggerating. So if you take like high end like luxury cars like your Audi or BMW, they have like thousands of microcontrollers in that, and they have operating systems and everything. So these are very complex systems. And now you can think about your flight control system or nuclear power plant or any other industrial automation system. So how these are going to get. And another important thing with these large scale systems are they are processing like very huge amount of data, right? So you need some kind of encoding decoding of these media things, or it could also be they should also have like security features. They should have cryptographic functionality. Okay, so those are very important with these systems. Any questions so far up to this?
No, sir.
Okay, cool. So coming to the application areas, so I think we saw in the introduction slide itself. So the applications are you can just name it and we will have an application. So if you take consumer electronics, we have camcorders, cameras, and all these things, and household appliances. Like I said, your TV, DVD player, washing machines, refrigerators, microwave oven, and then you have your home automation and security systems. You have air conditioners, sprinklers, intruder detection, and CCTVs, fire alarms. And then you have your automotive industry, where you have your anti-lock braking systems that we saw earlier, your engine control, ignition systems, automatic navigation systems, and much more. And then you have your telecom, your cell phones, phone switches, handset, multimedia applications. And if you take computer peripherals, your printer, scanner, fax machines, all these things also have your embedded system in this. And then you have your networking systems, you have your routers, switches, hubs, firewalls. And then coming to healthcare, you have scanners, EEG, ECG. And measurement and instrumentation, you have your digital multimeters, your CROs, that whatever device that you see in your microcontrollers lab, right? So your logic analyzers, PLCs. And then of course we have your banking system, your ATMs, currency counters, point of scales. And then your card readers, your barcode readers, smart card readers, and other handheld devices where we swipe our credit cards. All these things, everything. So wherever you see a microcontroller, any chip that goes, that becomes an embedded computing device. Okay, so the applications are just many. Next is purpose of embedded systems. So we have different purposes. So let's quickly go over one over the other. So the first is data collection, storage, and representation. So we have your acquisition of data. So how you get the data, right? And then what do you do with it? Whether you store it, and then you permanently store it, or you temporarily store it, or you don't store it at all. So based on this, so first you have your different data sources. Like one is your text, it could be your voice, image, video, or it be electrical signals, or anything else that can be measured. So that becomes your data. And like I said, coming to the storage, in some systems you temporarily store. Like for example, if you take digital TVs, right? Like early versions of digital TVs, they did not have like dedicated storage. So what they do is they take whatever you want to display, they put it onto the frame buffer, and it displays whatever is in the frame buffer, and then on the screen. And then it discards that frame completely. You don't store it anywhere. So what, that one frame is just lost. After it is rendered, it's lost, that's all. But then it may not be true for all the applications, right? Like for example, if you take digital cameras, you click on a photo, it has to store the photo. So you need like some kind of a memory in your system there. And these days even digital TVs have your storage. You can record things like that, right? But anyway, so get the idea. The other thing is about things like your CROs, right? So where you don't need to store anything. If you want to store, you need to like attach some kind of an external device and then you transfer the data. It's like that. So so it's just so these devices just display the data and they render it and then they discard it. They don't need it anymore. And coming to the representation, so this is how the data is represented to the user. So these embedded computers, their purpose is to render something to the user. Again, the examples include your digital TV and digital cameras. Their sole purpose is to show something to the outside world, to the humans or to the users, for them to perceive. The next thing is about data communication. I think you guys would already know about this. So data communication can be a very simple home network to complex satellite communication, and these can be simple. I mean, wireless to wired. So it can be Bluetooth or Zigbee or Wi-Fi, Edge, GPRS in the wireless side, and in wired side, these could be your RS-232, USB, TCP/IP, PS2, and things like that. So then we have a digital or a data and signal processing. So these embedded systems purpose is to process streaming data. So these could be video or audio streaming data. A typical example would include the digital hearing aid or your a mic connected to your speakers, right? So it processes the speech. Speech is actually a signal, the audio signal, and similarly it could be video signal too. So video signal, you have to process it, and then so these are what you need to keep in mind is these are streaming data that you need to process. The other one is about monitoring. So these devices are it is about monitoring some signals, some electrical signals you monitor. Okay, so examples of this include your EEG, ECG, your CRO, and digital multimeters. So here you use your sensors. So there will be some sensors that you use to collect the information. So you have your probes, or you have your sensor attached to the human body that actually measures electrical signals. Then you have your control based systems, right? So it uses sensors and actuators. So the sensors are the devices that collect the data. These are the input devices, and actuators are the output devices that actually do something physical. So the sensors and actuators act as the input and output device to these embedded systems. If you take example of the air conditioner system, temperature sensor is your input device, right? So its purpose is to measure the room temperature, and then you take the actuator part. It could be like a relay that adjusts some knobs, or it could be like changing the speed of the motor, right? So the motor becomes the actuator here. So that will be your input and output device here. And I just want to point out the two figures here apart from the AC, the normal AC that we have at home, right? So the one here is the high. It's called HVAC. It's a very high end AC that is used in big corporates or even like in factories and big infrastructures. And to just give you a scale of how big this is, right? So you look at this, and these small dots almost like they correspond to say like one human or something. These are not humans, but I'm just saying that's how small we are compared to these HVACs. Okay, so that this is, if you look at it, how grand is it, right? It is, right? So you have computing device that controls the parameters of these HVACs. And then we have your application specific user interface. So this is about the user interface part, so where you have to interact with the user. So you need input and output devices like your input device like your buttons, keypads, switches, uh, so your microphones, cameras, and all these things. And then your output device is your LED, LCD, your speakers, and then vibration alerts and things like that. Okay, so yeah, with this we come to the end of the introduction to your embedded systems. So any questions you guys have?
No, sir.
Okay. It's actually quite straightforward. I think it's a very simple, and I just want to make it a little interesting for you guys, because you get motivated about the rest of the subject, right? Okay, so now let me check if I can take your attendance here. Not sure how to use this thing, man. So you guys can go ahead and say present. Let me open the chat window here. Okay, you can start typing present in the screen, so that I will work offline and I'll mark your attendance. Okay, so yeah, go on. Okay, meanwhile, guys, have any questions or anything, any concerns about the streaming or anything else? Uh, Please feel free to discuss. Aman Kapoor, it takes a lot of data. So, what is it? What's the concern here, Aman? Aman Kapoor? Ah, yeah, got it. Yeah, yeah. Okay. So, w- see, so this entire online thing and marking this attendance, right? So all these are VTU mandated things that we are doing. It's not like something that we have come up with. So we are just following what has been instructed to us. Having said that, it will be good if you guys can inform us ahead if you cannot make it to the live classes. Okay, and then if even if it offline, if you can if you can view the videos or something, or you can somehow fix a time where you can see the recorded videos, or go over the assignment and things like that, then it'll be good. So does that work? Oh my god, it takes a lot of time. Yeah, you can. uh,
Class, class.
okay, yeah, we do have recorded lectures, right?
నువ్వు తిడతా
Okay, anyway, if you can, you can you can drop a mail to me. Okay, so from your side also, if you can try to contact VTU, then that's okay with us. um, you can also write a mail to me, and I can forward it to the principal, and discuss it with him what can be done. Okay, 2 to 3 classes for a day is good enough. Yeah, right. Yeah, that's what we are having, right? Like 3 classes. Hmm. Okay, so anyway, if you have any concern, we'll see how it goes for the next few days. Then you can actually you also can think about it, and see how things are. going with you, right? And if you really find it difficult, then you can draft one mail and you can send it to me. I'll discuss the same with the principal and we'll see what we can do. Who's that? What is it? I'm not able to hear. Yeah, what is it? Was there anything? Okay. So yeah, we'll like I said, right? So we'll see how it goes for the next few days. Then we'll see if we can alter the timings and do something about it. Okay. All right. So everyone gave attendance, right? So all 159 of you. Semester exams. Um, we haven't heard anything from VTU yet, but they have not mentioned anything about postponement or canceling of exams too. So we are assuming, since we have not heard anything, we are just thinking that it's going to be uh, as on schedule. So we don't know. We just have to assume that. Hardware part of the lab, I think everyone suffers the same problem, right? So yeah, what about revals? Revals, I thought you guys have applied for revals already. Less syllabus or something. Less syllabus, huh? No, I don't think so. I don't think that's happening. The hardware part of the lab, right now we can't work on that. So we'll just have to raise our concern. Oh, reval did not come, is it? Okay, let me get back on that, on the reval part. Okay. Okay. I'll check on the reval part and I'll get back. Okay. Fine. Okay, so I'm going to stop recording. So I hope all of you gave your attendance. All right, 3, 2, 1.